We've all seen how amazing large language models are at talking like us, right? They can write emails, poems, you name it. But what happens when we need them to talk to a computer, to speak in code? Well, that's where things get messy. Getting an LLM to generate perfectly structured, syntactically correct data every single time has been this huge, slow, frustrating challenge. Well, until now.
So in this explainer, we're diving deep into a crazy breakthrough called XGrammar. Here's the game plan. We'll start by looking at the core problem with structured data. Then, we'll uncover the really inefficient bottleneck that's been holding everything back. After that, we'll get to the fun part. XGrammar's super clever shortcut. Take a peek under the hood to see how it works, and finally, check out the absolutely ludicrous results.
All right, first up, the structured output problem. Let's really dig into why getting clean, reliable data from a super smart AI is so much harder than you'd think.
I mean, it sounds simple enough, doesn't it? If a model can write a Shakespearean sonnet, you'd think spitting out some perfectly formatted JSON would be a piece of cake. But the very thing that makes them so creative and flexible with human language is exactly what makes them kind of bad at the rigid, unforgiving rules of machine language.
And this right here shows you the problem in a nutshell. On the left, you've got a perfectly friendly, human-readable sentence. We get it instantly. But to a software application, that's just a bunch of noise. What the app actually needs to, do its job is the clean, structured JSON on the right. No mistakes, no extra words, just pure data.
So the way we've been trying to fix this is with something called constrained decoding. The best way to think about it is like putting guardrails on the LLM. Every single time it goes to pick the next word or piece of a word, what we call a token, this process jumps in. It checks all the possible options and blocks or masks any token that would break the formatting rules. It basically forces the model to stay in its lane.
It sounds like a pretty smart idea, right? Just force the AI to follow the rules. But, and this is a big but, those guardrails come at an absolutely staggering cost to performance. It creates this massive, system-slowing bottleneck.
To really understand why it's so slow, you got to start with this number, 128,000. That's roughly how big the vocabulary is for a model like Llama 3. So for every single token it generates, it's picking from a list of 128,000 possibilities. And this is what creates that insane bottleneck. Imagine that bouncer. Every time a new person walks up to the rope, he has to read the entire massive rulebook and check it against every single person on his 128,000-person guest list. It's just unbelievably inefficient.
Yeah, this whole process is just a painful, brute force grind. For every single token the model wants to output, the system has to go through this whole song and dance on the CPU, checking the full vocabulary, one by one. It can bring the whole operation to a screeching halt.
Okay, but this is where it all changes. This is where it gets really, really cool. Let's talk about XGrammar's incredibly clever aha moment that just completely shatters this bottleneck.
The absolute genius of XGrammar is that they realized checking all 128,000 tokens every single time isn't just slow, it's completely pointless. They saw that not all tokens are created equal. So instead of brute force, they went with a much, much smarter strategy: divide and conquer.
Here's their big insight. They split the entire vocabulary into two buckets. In the first bucket, you have context-independent tokens. This is the huge majority of them, and you can figure out if they're valid ahead of time and just store the answer in a cache for a super fast lookup. Then, in the other bucket, you have the few, tricky, context-dependent tokens. These are the only ones that need that slow, careful check during generation.
And when you look at the numbers for a really common task, like generating JSON, it is just wild. It turns out that over 99% of the entire vocabulary falls into that easy-to-check, pre-computable category. Less than 1% of all possible tokens actually need that slow runtime check. XGrammar basically tells the system, hey, just ignore that 99% and focus on the tiny little slice that actually matters.
So this is a fantastic idea, right? But how do you actually build an engine that can do this so dang efficiently? Let's take a quick peek under the hood.
It's not just one magic trick. It's a whole toolkit of optimizations. They use a really smart adaptive cache and some clever context analysis to drastically shrink the number of tokens that even need to be looked at. Then, for the work that's left, they use an efficient stack and overlap the CPU and GPU work, so there's literally no wasted time.
All right, so we've seen the problem, we've seen the brilliant solution. So what does this actually mean in the real world? This is where it gets absolutely mind-blowing. When you put all of this together, the result is just wow. XGrammar can generate these validation masks up to 100 times faster than the previous state-of-the-art. That isn't just a little bit better, that's a total game changer. I mean, just look at this chart. The performance gap is almost hard to wrap your head around. That tiny blue bar for XGrammar on the left is so small you can barely see it. We're talking 52 microseconds. Compare that to over 18,000 for a popular library like Outlines, or a jaw-dropping 380,000 for Llama.cpp's engine. It's not even in the same league.
And maybe the best part of all, when you actually plug this into a real-world LLM system, the overhead is basically zero. The time it takes per token is almost exactly the same with or without XGrammar. So you get all the benefits of perfect structured output for essentially free. It costs you nothing.
And this goes way beyond just speed. Without these kinds of guardrails, even a top-tier model can fail to produce valid JSON almost 40% of the time. Maybe it adds a friendly "here's the JSON you asked for" at the beginning. With XGrammar, that failure rate is zero. You get perfect, parsable, machine-readable output, guaranteed every single time.
So the big takeaway here is that this isn't just some minor optimization. By making the conversation between an LLM and other software instantaneous and totally reliable, it just unlocks so much new potential. This is a fundamental building block for the next generation of powerful, dependable AI agents.
And that really leaves us with this final, massive question. For years, we've had this slow, clunky, unreliable translation layer between the fuzzy world of human language and the precise world of code. Now that XGrammar is making that friction basically disappear, what new abilities are we going to build? What becomes possible when our AI can finally speak the language of machines just as fluently as it speaks our own?